Alrighty, good morning and welcome. Actually, let's go back this way. Yeah. Hold on, where's my stylus here? Stylus, where did you go? Okay, well, let's go ahead and get started today. So we have a number of, it looks like, questions that have been posted in Discord. So I'm glad. That means we have something to do, which is always nice. So with that, let's go ahead. So our first question is, I see a lot of questions wanting to go through 7 through 11 and possibly 12, and then 1, 2, 7, 16, 17, and 20. Okay. And then the patient question. So let me go ahead and make sure that we're all on the same page here. So I'm going to go ahead and look at the exam 3 document here. That's the one that we're going to be looking at. And so let's just start in kind of numerical order here. So I think let's start with number 1. We'll do 1, 2, and then 7 through 12, 16, 17, and 20. All right. So with that, let's see. I need to I have to turn on finger drawing until I can find where the heck the stylus went. That's always the trouble with tablets, right? Alrighty, we're going to attempt this. So the first question, number 1. I guess this is going to be a little uglier than normal too, but that's okay. We'll make do. What is the molality of 31.6 grams of ethanol dissolved in 60 grams of water? So molality. Oh gosh. Molality. Okay, I really need to find where the stylus is gone. I can't I can't work like this. I found it. Okay. We will turn off finger drawing so I don't have any more issues. No, go away. Okay, found the stylus. We're good. Okay, so molality, oh, that's so much better, is moles of solute per kilogram of solvent. Right, so this one kind of just comes down to, can you identify the solute and solvent and then perform any conversions necessary to get them into these units. So it looks like in this case we're going to have ethanol and water. We have 31.6 grams of this, and we have 60 grams of water. And so doing this, we want to identify that the solute is ethanol, right? So we're given that we have 31.6 grams. We're going to use its molar mass, which I think is something like 46 point something grams for 1 mole. Not really wanting to do the crazy adding here. Okay, so we bust out our handy dandy calculator. 31.6 divided by 46. And we get roughly 0.68670, we'll say. Even though it's 3 sig figs. For the kilograms of solvent, we're given grams of water, so we want to convert that to kilograms. So we're going to want to put another grams on bottom, 1 kilogram. Hopefully by now kilo and milli should be like very easy for you to do in your head, I would hope. And so we get that many kilograms. And so when we do the division here, looking at the answer choices, there's really only one that makes sense mathematically, and that should be 11.4. Because you see it's roughly an order of 10, a little bit bigger. So. But you can do that with your calculator. So there we go. And of course, units for that would be moles per kilogram, or you might just say 11.4 molal with the squiggly m. Okay, so hopefully that one, good morning, clears up. I don't know why. Oh, I see. Oh, I didn't see the morning. Hopefully that clears up that question. Number 2 asks us to Where did I just put this exam? There it is. What's the freezing point? So essentially during this sort of exam, whenever I gave this, I would have constants on the board. So you would find the KF for ethanol, which I'll just Google right now. I'm sorry, KF for, I'm sorry, this is water, is it not? And that should be 1.86, right? Okay. Yep. So it is indeed 1.86. Alright, and so remembering that the freezing point, the change in freezing point is equal to I times KF times squiggly m, and we'll put a negative sign in there. Again, sometimes you see that KF value will be negative. You just want your answer to be negative overall. So with this, we're just going to plug in stuff. We know because ethanol is covalent, that it's going to have an I equal to 1. It should be soluble but not dissociate. So we'll have an I of 1. KF is given to us. And then the molality we calculated before. So delta TF should equal negative 1.86 times, I guess I should put a 1 in there, and then we have the 11.4. Doing this, we end up with negative 21.2 degrees Celsius. And we know that our original freezing point of water is 0. So we're looking at temperature final minus the initial one is negative 21.2 minus 0. And so our answer is just negative 21.2. Ta-da! That's actually vodka, just so you know. So that is the freezing point of vodka. That's why it freezes so low in terms of temperature. So it has to be a really, really cold freezer. Most freezers operate a little bit higher than negative 20 degrees Celsius. Alright, so okay, looks like now we're going to go through the lovely 7 through 12 here. This is all just kind of one continuous problem. The way that this exam worked, by the way, just so you're not terrified of it, you'll see that some of these questions do depend on your answer for the previous question. How I had the system work at the time I administered this exam was we would use little like kind of like lottery ticket type scantrons where you would scratch off and see if you got the answer right, and you would keep trying the question until you did get it right, and so you would know the answer going into the next problem. So like if you got number 1 wrong on a normal exam, if you got number 1 wrong, you would by default get number 2 wrong, right? Because you didn't have the right molality. But that's why this sort of thing happens here. So I avoid that, of course, in the exam is giving you, because we do not have that opportunity. So you'll see that this one is also kind of a similar idea where there are things based on each other. So here we go. We're using this paragraph of text before questions 7 through 12. Alright, so questions 7 through 12. We're told that we have 100 grams of benzene. We're heating from negative 50 degrees Celsius, I think there's 366 there, yeah, to 150 degrees Celsius. We have the freezing point or melting point is 5.53. The boiling point is 80.1 degrees Celsius. Enthalpy of vaporization, that's delta H VAP, that is 30.77 kilojoules per mole. There's a lot of constants here because this information is being used for like 6 questions, so that's why there's so many. Enthalpy of fusion is given as 9.9 kilojoules per mole. And then we're given its specific heat capacities for solid, liquid, and gas. So solid is given as 118.4, and these are all in joules per mole, degrees Celsius. Liquid, oh my gosh, so many numbers. Liquid is 134.8. And then the last one, the gas one, is 82.34. Okay, now that we've written down all of these numbers, wow, tons of stuff, we're told that we're going to kind of refer to some of these parts as A to B, C to D, and E to F. And so we might want to construct a graph to kind of help out with this. So if we want to look at a graph of what might be happening here, we're heating this from negative 50 to 150, right? We remember temperatures on this side. Oops. Temperatures on this side, and then the energy is on the x-axis here. We're going from negative 50 to 150 degrees Celsius, so those will be our minimum and maximum. And so we're going to start off, of course, at negative 50. We're expecting benzene to be a solid, right, because it melts at 5 degrees Celsius. So we're going to expect it's going to be a solid until it hits 5.53 degrees Celsius. That's what its freezing point is, or its melting point, same temperature. And we're told that this is going to be marked as A to B. All right. If we remember, we also will need some sort of period here where we're going to be applying heat that's going to go into melting, not changing the temperature. All right, the next phase we have is C to D, which is liquid. And if we want to think of when it's liquid, benzene is liquid in between its melting point and its boiling point, right? Above the boiling point, it's a gas. Below the melting point, it's a solid. So it's going to be liquid in between those two numbers. And it's told that the boiling point is 80.1. Oops. So we know we're going to have a liquid between 5.53 and 80.1. So this would be our C to D part of the graph. And then again, we're going to have a similar thing. We're going to have the boiling energy there. And then we're going to have the last one where we're going from our 81 degrees, 80.1, all the way to the top, which is the 150 up there. So that's kind of the hard part of this, is being able to translate all of these numbers that are given to us into some sort of representation, perhaps. So again, because this is 6 questions in one, right? So that's why this is going to take a little bit of time. So looking at that, remember that when we have solid, liquid, and gas, that means in between we have the kind of combined states, the melting and boiling processes. If we remember, there are formulas that will tell us the energy required at different states. If you remember that if you are for one state, if you're at one state of matter only, you use the MCAT formula. For changes, that it would be boiling or freezing, we would use delta H instead, right? So, thankfully for us, these ones are provided, so we're okay. We don't even have to worry about the phase changes. Those we can just calculate right away. We know C. We have the C for all the various states of matter. And we're going to have our amount. But the delta T is going to be the different part here. That may not be so obvious to us. And so let's take a look at this graph and see if we can't find the delta T's for these. So if we look at when it's a solid, This delta T is going to be the temperature during which it's a solid throughout this process here. So if we are going to end at 5.53, that's when it's going to start to melt. And we're starting at negative 50. That means our delta T will be 55.3. I'm sorry, 55.53. I don't know how to add. Oops. Let's fix that. If we look at what our delta T for the liquid is going to be, we're going to end at 80.1 because that's when it starts boiling. And we're going to start at 5.53, which is 80.1 divided by 5.53, 74.57. We should probably note our sig figs with these. And then the last delta T we're going to be working with is going to be ending at 150, and we're subtracting 80.1, which will equal. I do suggest, by the way, when you're watching this or doing these, actually do it on your calculator. Like, make sure, again, you're in good kind of like muscle memory with your calculator, whatever calculator you use. Just, every little bit helps, right? So I would definitely suggest that. Okay, so we have everything we need now, except for one little bit. But all we're going to do now is 5 calculations at once. That's question 7, 8, 9, 10, 11. And then we just add them up to get question 12. So let's go ahead and look at one last thing here. Notice that the units for all of these energy values are joules per mole of some sort. However, we're given grams, so we're going to need to work with that first. So, last thing, the M needs to be in moles because all of our conversion factors are in moles. So let's take that 100 grams. Benzene's molar mass, 12.01 times 6 plus 1.008 times 6, 78.1. Okay. And then let's just go ahead and inverse that. All right, and so we get 1.28 moles as a result. Okay, now we can actually do this stuff. So again, hard part of this is just setting it up and kind of understanding what's going on, and that may take a few minutes. I'm obviously not going to have something like this on your exam because just the time limits and the fact that it's going to like randomize the question order and all that. You're not going to have to do 5 calculations for one problem like this, so don't worry. You'll be given like, okay, what's the calculate Q at C to D or something. So you'll just be kind of looking at one little bit at a time. So, but this is still good practice. So, question 7, all of these are kind of in order. So we're looking at essentially 5 phases here. We have the solid plus liquid, the liquid plus gas, and then the gas portions of this graph. And so if we want to look at the solid part, the Q will be equal to the amount times our specific heat for solid and then the change in temperature. So we'll have our 1.28 there. Our CS for CS is 118.4. And then our delta T, which we already calculated, was 55.53 degrees Celsius. Note, as always, units should cancel. We're left with joules. We do this and we get, I think, I'll just do it. Okay, 1.28 times 118.4 times 55.3. We get 8415, which, looking at the answer choices there, is going to just be the 8410 answer. Probably just some sig figs there. I'm going to just move this stuff down because I'm out of room. So Q will equal to 84, well, with sig figs, we'll round it. So we'll just be good with that. And that's in joules. Exciting. Now to the melting one. Remember, for transitions, we're just using the amount and the delta H. So that's 1.28 moles. And then we have the delta H for fusion is 9.9. But notice that the units there are kilojoules per mole. So our answer for this is 12.672 kilojoules. So we'll need to round that to 3 sig figs. So 12.7 kilojoules. But since the question does want it in joules, just to make sure our units are consistent, we can just go ahead and do that. So we'll just put that in joules. And so that one answer should be A. Next one we're going to have is just liquid. So back to MCAT. Remember, you use MCAT whenever you have one state of matter at a time. So that'll be 1.28 moles. Our C for liquid is 134.8. And then our delta T was 74.57 degrees Celsius. Of course, if any questions come up like, why the hell is that 74 again? I am happy to talk that over again. So just let me know. Otherwise, I'll just keep here punching my calculator. Punching numbers into it, rather. I'm not going to physically abuse my calculator. I love my calculator. Okay, so doing this stuff, we get, with the appropriate number of sig figs, we get 129 probably. Hopefully that's an answer, so it is. Solid or liquid plus gas now. As you can see, this sort of calculation is rather repetitive, but that's okay. 1.28 moles. And then the delta H for vaporization was 30.77 kilojoules per mole. And so we'll end up getting 1.28 times 30.77. If we put this into regular joules, we get 39. 1, 2, 3, yeah, that many joules. 39,000. And then the last one, the gas phase only, back to MCAT. And so we have 1.28. You go all the way up. C for gas is 82.44. And then we had our delta T, which was 69.9. Doing all this fun stuff. Oof. 1.28 times 82.44 times 69.9. We get 7380 joules. Alrighty. No problem, I'm happy to do it. Okay, so that was numbers 7 through 11. Number 12, we just have to add them all up. It's just asking what's the total heat in kilojoules. So just pay attention to the units there. So we just have to add them all up. and then convert to kilojoules, or we can convert them to kilojoules first and then add them up. It doesn't really matter. Uh, that works. So hopefully this one you can do, but let's go ahead and do it. So we have 8410. Ideally you would use the non-rounded numbers for this, but I'm feeling lazy right now. 12,900, 39,400, and then 7380. Okay. Okay. So 0, 2, carry the 1, 5, 12, 21, 25, 28, 10, 12, 14, 23, 30, 4, 5, 8. You do all this fun stuff, you get some crazy number like this. Looking with sig figs, if this is indeed what we have, it should round to 800 joules, which would be the same thing as 80.8 kilojoules. Long problem. 5 problems, 6 problems. Yeah, 6 problems. So there we have it. So, woo, we did it. And exciting. So remember, this is not something I can necessarily do very easily for you on this exam. So you'll be able to, or you'll want to be able to essentially perform at least one of these calculations. So if I ask you, as benzene is heated from -50 to 150 or whatever, what amount of heat is used to, put into the liquid only phase or something, or how much energy is required to melt it. So it just kind of comes down to, can you piece together? Yeah, we can do 23. Yeah, you just kind of want to piece together the information you have and try to your best to identify kind of this sort of graph really helps with this sort of question, in my opinion. Just having it organized makes it very easy to see. Okay, yep, not this problem, these problems, 6 of them. Yeah, okay, good. Yeah, so the graph helps a lot. So once you can identify that, like identifying that you put your melting and boiling points on here, and those are kind of your areas where you flatline, those are the kind of subtleties here. So that's my suggestion, is if you can kind of master this sort of graph, you'll have no trouble in any sort of problem like this. So, hooray. Okay. Any other questions on that one? All right. So next, let's go ahead and do, I think next, yeah, of course. Okay, so next, chronologically speaking, I think is 16. So let's go ahead and scroll down to that. Oh, thank goodness. Okay. So 16, this is something I can do. It's not going to take us 20 minutes. So that's good. So 16, which of these is the strongest electrolyte when dissolved in water to a concentration of 1 molar? So we're looking at the strongest electrolyte. And that means it's going to break into the most particles when we dissolve it. And so that's going to basically, we're looking for the biggest I value here. That's what we're looking for. So let's go ahead and look at our options here. So we have aluminum nitrate. Oh, nitrate. We have calcium chloride. We have acetic acid. We have glucose. and then we have sodium chloride. So what we're looking for is the I value for these. So if we break aluminum nitrate up, we get an I of 4, right? We have 1 aluminum, 3 nitrates. What you can do is just add the subscripts up. So we have 1 aluminum, 3 nitrates. Add those up, you get 4. Calcium chloride, 1 calcium, 2 chlorides, I equals 3. For acetic acid, that's a weak acid, but it's going to be somewhere between 1 and 2. We don't quite know. Remember, with weak electrolytes, I mean, it's asking what's the strongest electrolyte, so hopefully the answer would not be a weak electrolyte. I hope. For glucose, that's an I of 1 because that's a non-electrolyte. It's just a molecular compound, not an ionic compound. And then sodium chloride is I of 2. So looking at these, we're going to say that aluminum nitrate is going to have the biggest I value. And so that one will be the strongest electrolyte. It's going to conduct the most electricity if we dissolve that for 1 molar in water. All right? Alrighty, let's see. Number 70. Cool. Okay, what will reduce the rate at which sodium chloride dissolves in water? So how are we going to make it slower to dissolve? If we stir the solution, well, that should make it dissolve faster, right? This is now going away from college chemistry to first grade real life. Of course, stirring the solution should make it dissolve faster. If we add more water, that should probably make it dissolve faster, because more water means you have less chance of it getting kind of like saturated nearby. Adding more sodium chloride, well, that probably is not going to help. So let's kind of put that on hold there. If we crush it into a fine powder, that's increasing the surface area, right? And so that's going to make it dissolve faster, right? We saw that, like if you were to take powdered sugar, granulated sugar, and rock candy, put them in water, the granulated sugar will dissolve pretty much instantly, and the rock candy is going to take 3 years to dissolve. So remember that more surface area means faster dissolving. And then heating the solution, we saw that heating typically makes things dissolve faster for solids, so we can go ahead and assume that that's going to be the case. So with this one, I would probably say, although it's not super obvious to us, adding more sodium chloride it'll actually slow down the rate of dissolution because you're going to have more stuff to compete with the water molecules there. So the more competition you have, the slower the process is going to be overall. So it's going to take more time to dissolve the sodium chloride just because you have more stuff going on in there. So the rest of them should increase it, make it dissolve faster. Okay, so just kind of a conceptual question there. All right, how about number 20? Partial pressure of blah, 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 blah. Okay. Forget number 17. We need to write everything. So number 20. So we have 30% argon, 40% helium, 15% nitrogen, 15% oxygen. What is partial pressure of argon in millimeters of mercury if the total pressure is 2.6 atmospheres? So we have a couple options here. We can convert our total pressure into millimeters of mercury, or we can wait and do that at the end. Doesn't matter, any of them will work. Let's keep it in atmospheres for now. Why not? Remember that the partial pressure of a gas will be equal to the mole fraction, the percentage, times the total pressure. So we're looking at, it's argon, right? That's what we're looking for, yeah. So we're looking at 2.6 atmospheres times 0.30, 30%, 0.30. So the partial pressure in atmospheres is 2.6 times 0.3, which will give us 0.78 atmospheres. We just need to convert this to millimeters of mercury. And that one we would use the conversion factor of 760 times 760, and we get 592.8, which will round to roughly 590, right? And I hope that's the answer. Yeah, looks like that's at least one of the choices. Hooray! Okay, is that clearer? Let's see, we have 20. Did that patient question towards the end? What the heck is the patient question? Oh, okay, I see. Cool. Okay, yeah, you can do it. You can convert it first. You should get the same answer. I mean, because mathematically, there are lots of ways to do one problem, and usually they'll all work out. Okay, so let's do 23 and then 25. Okay. Oh, it's the same mixture, but this time we're going to calculate the partial pressure of oxygen. So we have 30% argon, 40% helium, 15% oxygen, 15% nitrogen. We have a pressure of helium is 1.61 atmospheres. The pressure of oxygen is who knows what. So, a couple of ways to go through this. One way might be to do a proportion, because you know that the pressure of a gas is proportional to its mole fraction, right? However many moles of the gas are in there will contribute a certain pressure. So what you could do is, or we can even put this way, this is helium, yeah, 40% equals X atmospheres. Are we in atmospheres here? In atmospheres, yeah. We could do it this way, cross multiply, get your answer. Or if we wanted to be a bit more systematic about it, we could do it this way. So we know that the partial pressure of helium is equal to the mole fraction of helium times the total pressure. And so the total pressure is going to be the partial pressure of helium over the mole fraction of helium. So 1.61 over 0.30, 40. And so we see that the, I meant to divide it. Okay, so we see that the total pressure is 4.025 atmospheres. And then now we can go ahead and work with this. So we know that the pressure of oxygen is the mole fraction of oxygen times the total pressure, which is going to be 0.15 times 4.025. And in either case, you should get the same answer. And so you'll get 0.60, how many, I guess 0.60, yeah, that'll work. Of course, it'll be atmospheres. That's not changed. Hooray! All right, how is that one? Okay, in that case, let's go ahead and look at the last one. And we're looking at 25 next. If a gas's temperature is doubled, volume decreased to 1/5, what happens to the pressure? Okay, so remember, questions like these make up numbers. And so we want to play around with fake numbers here. So a gas's temperature is doubled. So let's go ahead. We know that we can set all of these parameters ourselves. Okay, so a gas's temperature is doubled. So let's just use 1 and 2. 10 and 20, 100 and 200, whatever, who cares, as long as it's doubled. Volume is decreased to 1/5. So let's say we start at 5 and then we end with 1. Or if you really wanted, you could just say we start with 1 and we end with 1/5. That's the same thing. Let's do that actually, why not? So we end up with 1/5. What happens to the pressure? So let's say we start with 1, and let's see what we get here. So P1 V1 T1 equals P2 V2 over T2. Thankfully, since we set all of our stuff to 1 on the left side, that's easy. 1 equals x times 0.2 over 2. So 1 equals 0.1x. X equals 10. So this tells us we are going to increase it by a factor of 10, right? So if our original pressure is 1, our final pressure is 10, we have multiplied it, or here, increased tenfold. It's always hard to say, like, not multiplying but not like doubling, you know, like we have nice words for double, triple, quadruple, but for 10 we don't have a fancy word for it, so just increase tenfold. Okay, so the last part here, I think, who was it who asked about this stuff? This was like a true false section I included. This is Cassandra or Cassie. So if you want to, awesome. Yeah, so for those ones, they look scary. Throw in fake numbers, choose the easiest numbers you can, and it'll all work out. Alright, so where are we here? With this one, it was a true-false little section here, so you could choose if it was true or false. If Cassie is here, is there a particular one you wanted to do? If not, we can go through them. I guess we have a little bit of time. So with this, let's go ahead. Why not? So the first one says that the mass percent of the solution is 9%. However, we're given that it's 0.90 grams per 100 milliliters. So if it's 0.90 grams per 100 mils of solution, and the density is 1 grams per mil, we're assuming 0.90 grams over 100 grams. If we do that, we get 0.9%. So number 1 should be false then, because it's in fact 0.9, not 9. The molarity is 0.15. Let's see. So we have 0.90 grams over 0.1 liters. Let's go ahead and convert that to moles per liter. We would use our molar mass. Let's see, 0.9 divided by 58.44. Indeed, we get 0.15. So this one will be true. Number 3 is if we dilute 0.1 of the solution to 1 liter, the molarity will be increased by a factor of 10. And that hopefully we can identify as false right away. It would be decreased by a factor of 10 because we're diluting it, right? So how would the concentration go up? I mean, that would be the opposite of what we're looking for. Saline is a strong electrolyte solution. We have an I of 2. So this is going to be a true statement. The solution will have stronger intermolecular forces than pure water. That's also true. We know that ion dipole forces are going to be stronger than plain old hydrogen bonding. We also know that the reason that things dissolve is because they will make stronger interactions than the pure solvent would by itself. Sodium chloride will dissolve in water because water is nonpolar. That's false because water is polar. Chloride ion mimics electron configuration of neon. So chloride ion's electron configuration is 1s2, 2s2, 2p6. Is chloride the second one? No, it's the third one. Or it's in the period 3. 3s2, 3p6. So which is the same thing as argon. So that one is false. Mass percent of oxygen in water is about 89. Zooming through these, by the way, just because these ones are kind of what I did this semester was I did a kind of like tried to keep you studying, keep things fresh in your mind the whole semester, so you would still have kind of older questions that were not worth as many points, but still like um, keep things going in your head. If you do this, you do get about 89%, by the way, so we can say that's true. Sodium chloride's chemical formula is SCl2. Hopefully we know that's false. This would be sodium chloride NaCl. And then there's two isotopes of chlorine, 35 and 37. Do they have the same number of protons? Yes, they do, because they have to be the same for them to be chlorines. So that one will also be true. So, hooray. And look, there's some naming to do too. You love naming. So, woo, we did it. Is there anything else you guys would like to go over? Now. If not, enjoy the rest of your spring break. So Monday will be your exam. Again, you'll have all day to do it. It's timed as always. Remember the topics are intermolecular forces, including that like boiling point stuff. We have the gases and then the solution chemistry. So those are going to be the areas that are on your exam. All right? Cool. Well, with that, enjoy the rest of your spring break. We'll see you on Tuesday.